So I'm just going to begin with the question, why are we even having this talk? To some it may be, because you've already looked into the field. For others it's, well, isn't machine learning, isn't it already interpretable? Well, in the beginning, that's the way it was. We had coefficients, all of this stuff, great. We can tell something about what the model's doing and maybe provide some kind of explanation. But things have changed. We now live in an era where it's all about the performance. And I don't know, is anybody here engaged in Kaggle? Just a few? Well, in Kaggle, basically, there's a leaderboard and you have an error metric and you just go for it to try and reduce that. Now, to do that, you basically end up with these things. Complex features, very complex models, and you have to search a very broad hyperparameter space in order to squeeze that percentage down. But it also squeezes the interpretability of the model. So, the question that might be asked more in a business context, let's say, is tell me about this prediction you're showing me. What's the basis of it? Rather than, oh, this has got 0.34% error. What does that mean? So that's what we're talking about when we look at interpretability. But you might think, well, is that just people being a bit fussy, rejecting new technologies? You do hear that kind of argument. Well, one example that shows that there is a serious side to this, a researcher called Rich Caruana in the US found that when they trained a deep learning model, I think it was, on some medical data, they were looking for what was the best approach to boost recovery rates. And the model that they had found that to be an asthma sufferer was the best thing, which seems a bit counterintuitive. Basically, it was a proxy for other things. But there was the danger in just letting this wonderful technology run away and the need, in their case, to build a more interpretable model to see what was going on and understand some strange results. So basically, 3 questions you might want to remember just tomorrow when you've forgotten the rest of it. What, how, and why? Well, it begins with the what. We're not excused data understanding and data quality. And that's both the variables, but also the quality of the actual observations, the influence they can have. How? Well, that's basically, to some degree, traditional interpretation, looking at the way the whole thing is working. The algorithm and the data, what's the general characteristics. But a focus in recent times really on the predictions, being able to explain more about them. So I'm just going to whiz through this bit. How well do you understand the data? Lots of questions which, hopefully for this audience, are not too strange when we're evaluating data. And I just want to mention one tool, and there are others, some great validation tools in R, but this one gives you a lot almost for free. With one line, you can get a whole report, and this is just a couple of samples that you get out of it. So rather than writing all of your code by hand, let's apply some technology and get some good results. But you've still got to apply yourself then to what does this mean, what are the correlations, etc., etc. Now, in terms of model interpretation, if you've looked into any of the literature, as always, there's the jargon. And they talk about model-specific and model-agnostic. What does that mean? Well, let's put it another way. Model-specific, basically, to some degree, knows something about the algorithm. It's built on top of it and is able to look inside, and from that, establish maybe which of the features is making a big difference. Whereas with an agnostic approach, you're taking an old engineering principle called system identification. Basically, you're wiggling the input to see what's going to come out the other side. And therefore, you can treat this as a black box, which is what these complex models effectively become. What's the scope of the model interpretation? So a different question to the type. Again, these terms are bandied around a lot. Global interpretation, local interpretation. Well, they're pretty vague terms. What they basically come down to are, again, taking the model as a whole, what are the average effects? Or the local level is generally meant the instance, the observation. Why this prediction given this vector of details? So let's think about the global first of all. First question is, what do you want to understand? Do you want to understand the importance? So if you were to put a rank of the features, which ones come to the top? That's often a key question, maybe from a business perspective, or if you think about a healthcare perspective. Or are you interested in something a bit more cute? do you want to see a relationship for this particular variable and the difference it will make? So individual effects. So the first tool I'd like to highlight is actually one is kind of an umbrella tool called Dialects, which is, I found out this month, actually being upgraded. There's a whole Dialects 2 movement going on. But it uses, as many libraries do, another library, VIP, Variable Importance Plot. And there's also just another call out to a model-specific explainer, which there aren't many of in this talk. I've focused on the agnostic, because they enable us to compare models. And that really becomes more important when we're trying to search for valid interpretations. But this is, the random forest explainer has got some very interesting things just in the context of the random forest library. But back to VIP, what's good about it? There's the word permutation. Getting back to that idea of system of identification, by permuting values, by changing them and observing the effect, it's able to work out what the feature importance is without knowing anything about what's going on in the algorithm. So the algorithm could be regression, could be random forest, could be a neural network. But it's looking at the in and the out. And from that, establishing some variable importance. So you may have seen these kind of plots. If you've used caret, from there you have, then it's quite easy, var-imp, and you've got some variable importances. But whereas caret might tend to work around knowing lots about each particular algorithm, this is again taking the agnostic approach, but enabling us to look at the same features applied to models and do a comparison. And you see, then you can see which ones are in common important and which ones are maybe just feeding up the characteristics of the algorithm. So that gives us a kind of a bit more confidence about interpretation. And that's an important point to stress, is when a product is put forward, it's often, oh, this is now interprets complex models. Not necessarily so securely. So by having different ones, you can kind of have a community of experts. And this is just one slide on that random forest explainer. This, because it knows about what it's looking at, here we've actually got a plot of two different types of importance measures. And you can start to see the relationship between the two. But to enable that, it needed to know how the tree splitting is working. So that might be one if you're particularly focused on trees. And if you're not focused on trees, the data-driven paper 2 years ago showed that trees generally perform best on tabular data when they did that survey of 165 different types. Now, the experienced ones will know, well, this is all right, but interactions. You know, we've got variables. We don't live in a linear world. And if you've got these things, when they're together, things change differently to just taking them one by one. Now, the IML package provides what's known as an H statistic. I think Friedman was proposed this quite a number of years ago. And it can do it different ways. This is just an example of if you're looking at two particular ones here, the crime, I think this is the Boston data set, and then against all the other variables and what the level of interaction is. So again, if this is maybe a more critical use case, and you've got some people with real domain expertise, they know what these variables do, then you're able to offer a little bit more insight into how your model is working. Now, in the days of just working with regression, LM, off we go, we've got those coefficients. Partial dependence plots kind of give us something like coefficients, but in a more complex scenario. And these are three libraries that do it, and I think there are others too. It's becoming more accepted as a technique. This particular slide, again, is comparing models and enabling us to see the difference for values when different models try and work out the relationship. So the simple linear model drives through, don't care much about this. But the other ones are detecting more information in the variable. So partial dependence, very worthwhile thing to have a look at. However, partial dependence is quite vulnerable to collinearity, as are quite a few techniques. And therefore, something called these accumulated local effects plots try and compensate a bit for that. Not quite as pretty, but you've basically got the same kind of idea. How is this varying over the possible values? Then again, you might want somebody who says, well, what if we changed? what if the value of the variable was different? What would the model do then? Well, that's what this next group of plots come. So we've got this Ceteris Paribus idea, Latin. Basically, it's just what if. And here's an example. And if you look at the Daleks package, you'll see there are, and the Ceteris sub-package, there are lots of possibilities with what you can do with this. But here again, we're able to compare across models. So again, more insight. If this variable had this value, what would this algorithm think about it? Now, what about local interpretation, getting down to the observation level? Who's heard of this package, Line? Okay, so maybe about 10, 15? Well, this, maybe if we mention the P word in the Python world, caused a big stir about 3 years ago when the authors not only put out their papers, but backed it up with a library. And people got very excited. So business jumped on and said, yes, Lime will now explain complex models. Truth is a little bit more refined than that. However, let's not take anything away. This was a great breakthrough. So what it does is it generates more data from the data that it's provided. It then does some complex model predictions around that, and from that tries to fit a local linear model. So quite a bit of machinery going on underneath to try and give you the most important features for this specific observation. And that's the kind of thing you get out. And nicely, it's also got its own little probability and explanation fit values. However, Lime, because of the linearity assumptions and a number of other things, is not so solid. So with some data sets, it will perform beautifully. With others, your mileage may vary. So, other methods. This one, over the last 2 years, has gained a lot of attention. Shapley values. So this comes from game theory, believe it or not, and tries to attribute across all the possible groupings and their order what the actual feature values are for the instance. And there's various implementations that you can look at. And again, you just get one of these nice little charts coming out. Problem is, to compute all those possibilities takes time. So there are some approximations, and it will work with some things and not with others, but it's probably one of the most solid techniques, but again is vulnerable to collinearity. Breakdown is an alternative, and there's a new I breakdown, because breakdown, again, very slow. If you tried it on, say, a data set with 100 columns, and you can't do much to get rid of them, you're going to be waiting a long time. Because, again, most of these techniques take a lot of computing. But I breakdown is an order of magnitude faster. And again, you're going to get something like this out. Something that maybe you can give to a domain expert or to another data scientist who doesn't need to spend hours looking at your work to say, what do you think about this? So a bit of interpretability, at least for an expert audience. Gotchas? This is now starting to bubble up in the IML literature. Okay, we've got interpretations, but people are examining these interpretations and finding issues. So there's some of the questions. But before any of that, what we've already mentioned, quality of data and interpretability of data. So in other words, if you do very complex feature engineering, then you're still going to be in an awkward situation. Why is something log transformed and something to the power of 5, whatever. Also, I've begun to appreciate more, if your model's not much good, the interpretations really aren't worth much. So no shortcuts, unfortunately. Variable importance could be several talks in itself. But basically that permutation thing is one of the best things that's come out, I think, in recent times. And if you go with, say, the defaults on a random forest library, the Gini impurity is the split criterion, that's not so valid always. So that might be worth a bit of research if you're wondering why we're looking at new techniques. And we've mentioned some of the others that can get you if you're thinking you put this into a pipeline. So the takeaways, use different models and use different approaches, and that will help you get through these questions. Consider the local, the instance, and the global, and see, does it make sense? And of course, as with many things, combining multiple perspectives gets you further. Just as a kind of postscript, there is still the opportunity, though, to use more understandable models that don't require all this post hoc work. So what do we mean by that? Well, here's something I've been looking at recently called pre-rule ensembles, where it generates directly in the training process rules from the data. Not necessarily as a sort of sub-post hoc modelling, but actually as part of it. And that will then lead to things like variable importance, and you'll be able to do interaction plots. So there's some recommendations for later if you take the slides. Lots of possibilities. So I think we've got a couple of minutes for questions.